let's begin the class today. Okay, so now I know your views. You have some partial idea about the slip system, so I will tell you. So it's a slip plane. Slip plane, see, in a crystalline material, you have a slip plane is nothing but but an atomic plane rather, which has got the highest planar density of atoms through which the dislocations can move by a distance which is equal to the Bugger's vector. So I just want to know from you one thing. What do you mean by a Bugger's vector? Anyone, please tell the. Have you any idea? Yes or no? Any idea about this thing?
Hello, sir.
Yeah, tell it.
Sir, the direction and magnitude of dislocation.
Okay, so slip direction. Okay, so what is the relation between slip direction and magnitude of dislocation? Correct. You are partly right, but what is like? Do you know exactly?
No, sir.
Okay, fine, good. Okay, no problem. So I'll tell you. So basically, what is the thing is that is as follows. So it's nothing but plane. First of all, you have to learn a plane because a direction can only be there on a certain atomic plane. And when there is an atomic plane, it is a plane which has got the highest planar density of atoms. What is the dislocations moved by distance equal to Burgess vector? So this is a simple thing. See, what is a Burgess vector? See, if you have a crystalline material with a atomic spacing equal to A, for example, if you have an atomic spacing of equal to A, now how the dislocations move. So dislocation is nothing but a missing line of atoms, right? It's a linear defect, 1D defect. So for the movement of dislocations, the distance by which the dislocations move. Okay, let's see. Someone has typed in the chat box. Just a second. Sure. Okay. I will explain. So first of all, we need to know what is a dislocation. So I think you have been taught about it. So I will not go that much into details. So a dislocation is nothing but a linear defect, right? Line defect or a missing line of atoms. It's nothing but a missing line of atoms, right? So if we say that, so when you deform the material plastically, like one of your friends said, during during plastic deformation in the material, so there is a certain component of shear stress which is going to act on a plane of atoms, right? Or rather on a number of planes of different atoms. So what happens is that so that the atoms in that case, if you deform the material plastically, what happens is that the every atom, I mean, in a certain plane, will be going to move. Such that the distance. They're going to move such that the minimum distance which is traveled by the atoms, actually, rather to say, so which is also termed as a Bugger's vector. So the Bugger's vector is the Burgess vector is nothing but the minimum distance traveled by the atoms on the slip plane in the slip direction during the plastic deformation. If plastic deformation occurs by slip, that is Burgers vector, actually. Okay, so if that is the case, so now the definition of slip plane stands very, very simple. It's nothing but so definitely, see, the slip cannot happen at all planes, because definitely for an atom to move to cover the shortest translational vector, or for the atom to move the minimum distance, the first criteria is that the plane of atoms, the atom has to be present in a plane which has got the highest planar density, right? So that the packing density, the packing fraction of atoms on that particular plane is very, very high, right? Correct. The first thing, slip plane. Okay, so now once we have the slip plane, we also need to know about the slip direction, because this is another component that is required to describe the slip system. So it's nothing. This direction is nothing but the direction present in the slip in the slip plane, or in the close packed plane, or the most close packed plane, which is having the highest linear density of atoms. Okay, so I think this you have been taught, I think, in your class. I roughly suppose that. So if you have the slip plane and slip direction, the slip system is basically nothing but the combination of the slip plane and the slip direction. So it's represented as HK UVW. So if the Miller indices of slip plane is HK and Miller indices of slip direction is UVW, so HK is represented in terms of the curly brackets, and slip direction is represented in terms of some arrow kind of a bracket. So that's what. So that is HK and UVW. Okay. So with this, so now let me ask you one thing. So do you have any idea about why dislocations can move only on certain plane? I said dislocations can move only by the shortest distance on certain plane and in certain direction. Like, do you guys have any idea about why this should happen? I mean, have you been taught any formula or something? I just want to know. Yes or no? Any guys can speak. You can unmute and speak yourselves. Feel free.
No, sir.
Okay, means okay. Got it. Sure. Okay, let me make it simple for you. Okay, sure. So see, this is actually the governing equation. See, for example, if you have tau Pn is nothing but a Pierce-Navarro stress. Okay, so that is equal to nothing but a product of the the shear modulus into negative exponential of 2 pi w by b. Now the question is, what is all these terms? So the first term is that the g is nothing but the shear modulus of the material. Okay, so that it's the shear modulus. I think you have an idea already. Now the what is this w is something which is new, the width of the dislocation, right? So, and b is nothing but the Burgers vector. When I was talking of b, so that is nothing but the Burgers vector. So here basically what you find is that here what you find is the width of the dislocation. So width of the dislocation is nothing but if you have a missing line of atoms. See, one of you have told that dislocation, there is a lattice distortion which is always associated with the presence of a dislocation, right? Because of course if you have, suppose the continuity of the play of the atomic plane is disturbed by one of the lines missing, what happens is that definitely there is going to be some strain, some localized strain in the material. When there is some localized strain, obviously the position of atoms is definitely going to shift here and there. I mean, the other atoms in the particular plane is definitely going to shift here and there. So, not exact. They will not be shifting randomly because this is again a crystalline material, but definitely there will be some distortion in the material. So, as a very simple way, so this is a very simple way of visualizing an edge dislocation, for example. Screw dislocation also you can visualize, but it's quite hard to visualize in that manner. So that's why people mostly try to visualize edge dislocations for as a result. So basically, what happens is that you see that if you have now a material which has got the width, so a width of see another thing is that a width of a dislocation is that region within a dislocation. It's a very it's we can call it the core of the dislocation also. Core is nothing but a center. Rather, I mean in English, core means center, right? So width of the core of a dislocation is nothing but the region wherein all the elasticity theory fails. There is no theory of elasticity that you can apply there, because around a dislocation you will have the strain field, right, that I told you, because due to lattice distortion. Now due to this lattice distortion, there will be two types of strains which are associated with the dislocation. The first one is the elastic strain and the other one is the inelastic strain. I mean, it's called the plastic strain rather. So when you move towards from the outer part of the dislocation towards the core of the dislocation, all your linear elasticity theory, okay, so all your elastic strain, in other words, fails, because there is no within the core of a dislocation you cannot be having at all the elastic strains at all. So it is not possible within the width of the dislocation. So once you don't have that, so what really occurs is that that this width that I have told you, this the W is, this is actually, it's not, I have not written it, you guys can note it down. So that is equal to A upon 1 minus mu. A is nothing but the atomic spacing on the atomic spacing in the slip direction. So in the slip direction, what is the atomic spacing is A. Okay, and B, I think I wrongly went through this B. I mean, I told the wrong way, thing of B, because B here is not the Burgers vector. B here is the distance between the slip planes. Okay, so the distance between the slip planes. So it's okay. So please make a correction. B is nothing but the distance between the slip planes, and W is basically the width of the dislocation, which is equal to A upon 1 minus mu. Mu is nothing but the Poisson's ratio, and A is nothing but the spacing between the atoms in the slip plane. No, I'm sorry, I also said but the wrong thing also there. So A is nothing but the distance between the atoms. Earlier I said in the slip direction, it's wrong. It is nothing but the space, I mean the spacing between the atoms, or the atomic spacing in the slip plane is A, and B is nothing but the the spacing, the interplanar spacing rather to say. Okay, so the interplanar spacing, B is nothing but here it is the interplanar spacing, but not in all cases. B can also mean the Burgers vector. It's not here, the B is not the Burgers vector, it's different. Okay, so from here, this formula, do you have any idea? Like, I want to know from you that if your W and B, I just want to ask you this. Okay, so you have got this idea, right? So for example, okay, some of you have joined now. Okay, fine. So fine. So basically, we were discussing. So Akyat, I think you have joined now. Okay, will you be able to?
Yes,
Yeah,
sir.
what will you be able to follow what I have already said, or you need to repeat this thing? But I
Sir, you
think
can
you
just
can.
repeat that like a bit fast.
Okay. Sure. I can just show you. It's very simple. I think you have been taught about slip plane, no? Slip plane, slip direction, and all. I think.
Yes,
Okay, good. So once you know, so it's a simple definition of a slip plane is what? It's a plane which has got the highest planar density of atoms, right? On which the dislocations can move, right? By a distance equal to Burgess vector. And I just want to know from you, do you know have any idea about what is a Burgess vector? No, can you define a
I just slightly forgot about that part.
Sure, no problem. See, the Burgers vector is nothing but the distance, minimum distance traveled by a dislocation on the slip plane in the slip direction, right? Because
Yes,
so see, dislocations. What is a dislocation first of all? Dislocation is a one-dimensional defect, and dislocations are carriers of plasticity. When you deform the material plastically, dislocations are there to manifest that plus the strain energy. You introduce a lot of strain in the material, and dislocations will obviously accommodate that strain, right? Correct, because
yes,
that's the physics behind this. So now, when the dislocations move on the slip plane, they cannot move by random distances because now we are talking of crystalline materials. They cannot move, by random distances. So definitely there has to be some basis. And dislocations, the minimum translational vector which is associated with the moment of dislocations on the slip plane in the slip direction. And translation vector, I mean the distance, minimum distance by which dislocations can move on the slip plane in the slip direction is termed as the Burgers vector, right? Got it?
yes.
Okay.
Understood that.
Yes. Okay. So definitely there will be a number of I have sent you. I think last week I have sent you some this some study materials. If you go if you happen to go through the study material, I think you can also see very good examples of the Bogus vector, good definitions, excellent definitions of Bogus vectors and so on. So that's there. So now if you have this, so that is obviously there, and then there's a slip plane and slip direction also getting defined very well. See, definitely dislocations cannot move on all planes. I've said. Now the question is, in a particular plane, can the dislocations move in all directions? This is again impossible. So for that, the dislocations can move only in that direction which has got the highest linear density. This class is actually not about explaining highest linear density. Maybe Professor Pradeep has explained this to you, I guess, right? Or not? Has this been explained to you?
Yes, I remember.
Okay, sure. So if that is explained, that is good. So if that is the case, so that's what we should see. An atom always see dislocation is nothing but it's at missing end of atom. So when you see that you say that dislocations are moving, dislocation will always energetically it is always favorable for a dislocation to move the minimum distance, no? The minimum distance because that will minimize the strain energy. I will show you this thing in a bit more details in the next slide. I will do that. So once you talk of the slip direction, so slip system is basically represented by what? It's represented by slip plane plus slip direction. And if the indices of slip plane is HKL by curly brackets, slip direction is UVW by this kind of arrow bracket. So you have this is the slip system. So slip system is represented by HKL UVW. No? Okay. So now I was talking of this Pierce-Navarro stress. So Pierce-Navarro stress. So the reason why a dislocation should move only in this particular plane can be very well explained from this equation. Only on the slip plane and the slip direction, because you see that in a particular. So if this is a W width of a dislocation, it's also termed as the core of a dislocation. This is only that region of a dislocation wherein the all the linear elasticity theory fails. You cannot use any linear elasticity theory at the width of the dislocation. It's called the center of the dislocation. Basically, people call it. And P is nothing but equal to the interplanar spacing. Okay, so B here is not the Burgers vector, it's the interplanar spacing here. And W is equal to A by 1 minus mu. A is nothing but the interatomic spacing on the slip plane, and mu is nothing but the Poisson's ratio. Right? Got it, right? This thing, you have made a note of it? Okay?
Yes, I made a note of it.
Okay, good. So when you have the W, so width of the dislocation. So from this equation, looking at this equation, can you tell me, for a slip plane, what should be the criteria? I mean, what should be the criteria for a slip plane? Because I said W equals to A by 1 minus mu, and for a slip direction, what should be the criteria? Can you tell correlate the slip plane and slip direction with these two terms actually? Tell that roughly. Anyone? Just let me see. You can speak. I mean, you can put your arguments. You can just speak. Unmute yourself and speak. No problem.
If the width of dislocation is equal to interplanar spacing, or
Yeah. Uh-huh. Uh,
so,
okay. Then. Yeah.
but then A by 1 minus mu should be equal to B. But then, so we
Yeah.
can,
Mm-hmm. Mm-hmm.
so then we have to see that the relationship between mu in terms of B and A.
Yeah, see, I will tell you, it's a simple thing. See, what you have said is if W is equal to B, what happens? G into e to the power of minus 2 pi. So, e to the power of minus 2 pi, I mean, that will give you something, I don't know, maybe you will get some value, okay, some different value. That is something which I have, see, my question was not that. See, for example, I told you that in the slip plane, what is there? Slip plane, I have already written the planar density of atoms has to be very, very high, no? I mean, the planar density of atoms has to be very high. So, in that case, I said W is equal to A by 1 minus mu, and A is nothing but the interatomic spacing in the slip plane, right? Interatomic spacing in the slip plane, and B is nothing but the interplanar spacing. So I told, so from this A and B, I mean W that is actually equal to A by 1 minus mu, that is A and B. Can you actually correlate what should be the characteristic of the slip plane and slip direction? Mm-hmm. Rough guess. Otherwise, I will tell you the answer. Rough guess. Anyone, please unmute. More ideas, please. Okay, I'll tell you. See, what happens is, see, in the slip plane, which is nothing but the plane with the highest planar density, na? So highest planar density means what? See, so highest planar density is something. See, I mean, I'm not going to discuss that much in details about the planar density and all, because then it will be a bit, the class will go on forever. So the planar density, you can also search in literature that slip plane, which is the plane with the highest planar density of atoms, is also the one which is the most widely spaced, right? I mean, it is wasn't given. So if it is the most widely spaced, then what happens is that the B is going to be what? B is going to be maximum, na? Because interplanar spacing is going to be maximum. Most widely spaced atoms, plane of atoms. So if B is very, very high, for the case of the slip plane, what happens? Your E, this denominator gets high, this total term reduces, right? So if this total term reduces, so yeah, so this what I was saying, I think I made some mistake. Let me correct it. Okay, I'm sorry. So if the slip plane, if the A, yeah, so just forget it. So I just made a small mistake, please don't mind it. So if that the spacing is very, very high, most widely spaced plane, that is correct. So if the most widely spaced plane, what happens is that W is equal to A by 1 minus mu. So that A, okay, so that A is going to be very, very high, because I already, like I said, that A is the interplanar spacing in between the planes, and B is nothing but the spacing between the atoms in the slip plane. Okay, I just reversed the definition. I made a mistake while doing the definitions. Please note this change. W is equal to A by 1 minus mu, and A is nothing but the spacing between the planes, okay, or the interplanar spacing, and B is nothing but the spacing between the atoms in the slip plane, correct? Now, if the spacing is maximum, this means A has to be very, very high. This means the width of the dislocation will be increased. Na? So the width of the dislocation will be increased. So this means if the A is very, very high, that is the spacing, interplanar spacing is maximum for the case of this planar density of atoms which are the most close packed. So so this is minus sign. So this will go to the denominator, and this total term will reduce. This total term will reduce, right? Got it, right? Yes or no? Please unmute and speak. If you're not understood, just tell me fast so that I can hear you. Hello? Yeah, please tell.
Sir, could you repeat it once?
Sure. No problem. See, I made a small mistake initially by telling that W is equal to A by 1 minus mu, and I defined A wrongly. I'm sorry for that. See, A is nothing but the spacing between the slip planes, and not slip planes, the spacing between the planes, or the interplanar spacing. If suppose this is a plane, this is a plane, the spacing between the planes is equal to A, okay, and B is nothing but the distance between the two atoms in a particular plane, right? So you have a plane here. I'm sorry. So okay, just a second. Yeah. So now suppose you have an atom here. You have a plane of atoms here. You have a plane of atoms here. So now the distance between the two planes is equal to A. Okay. So the W is equal to A by 1 minus mu. So A is the distance. Okay. And B is, suppose you have the atomic planes here. So the spacing between the atoms in a particular plane is equal to B. Okay. So that is the definition. So I think now you got it right. No.
Yes, sir.
Okay, okay, good. So fine. So now what happens is that, so if you have the planar density to be very, very high, yeah, planar density to be very, very high. Actually, these planes are the ones which are the most widely spaced. Okay, what are the most widely spaced? But what do I mean? I mean that A has to be very, very high, right? Then this means A has to be very, very high. The spacing between the planes has to be very, very high. If the spacing between the planes is very high, so that is something that qualifies as a slip plane. But that is only not enough, because there is another term, B. What is this B? So direction having the highest linear density of atoms. So if the linear density of atoms is very, very high, okay. So what happens is the spacing between the atoms will reduce, right? If the spacing between the atoms will be reduced, so this will B will definitely go down, right? B should go down. So if the B goes down and A goes high, what happens is that this total term 2 pi W by B, okay, so this total term increases, right? This total term increases. Now G by E to the power, now this is actually minus, this total term increases means this total, I mean this Pierce-Navarro stress, this is nothing but the stress which is required to required for a dislocation to travel on the slip plane in the slip direction. Okay, so this is the definition. So now if this is going to be very, very high, this term is going to be very, very high, this means tau PL should reduce, because this is minus sign. So they should drastically reduce. Now as it is drastically reducing, that is the reason why slip cannot happen in random plane, rather it can happen only on slip plane and in the slip direction. This is the logic, this is the basic logic behind slip, considering slip on a particular slip plane and slip direction. I think guys you got it right, you got the idea, no? Yes.
So basically, the A it must go very less than B.
No. That's what. See, A. I said that A now, like I corrected it. A is nothing but the spacing between the planes, right? So now the spacing between the planes. See, the question is the planes which have the highest linear
Yes, sir.
of atoms, right? So you can actually prove it that there are. See the plane, the interplanar spacing between all planes will not be the same, na? For example, 111 plane, 200 plane, 222 planes. So between the all the different planes, the planar the distance will not be the equal at all. So now the question is, so you will be able to prove actually that if you consider the volume to be constant, okay, the total volume to be constant, so the planes which have got the highest planar density are actually the planes which are the most widely spaced. I said so. Most widely spaced is going to be very, very high, correct? And so A is going to be high. This
Yes,
means this
sir.
term is going to increase, right? Because W is equal to A by 1 minus mu. So that's there. And slip direction is nothing but you have in a particular plane the atoms, the number of atoms placed. So if the planar, I said linear density on the particular plane is very, very high, because a plane can have many directions, na? It can have infinite directions. So only in that particular
Yes, sir.
direction, so only in that particular direction wherein the linear density will be very, very high. This means what? The linear density is high means the spacing between the atoms reduces. Na? Atoms. I'm talking of atoms, not planes. Now I'm talking of atoms on a particular plane. So
Yes, sir.
spacing between the atoms reduces. Spacing between the atoms reduces means this reduces. So if this reduces, this increases. Means this term is going to increase. Na? This total mathematical term. This term is going to increase. Na? If that is increasing,
Yes, sir.
this is minus. This is minus. So this means this is going to drastically go down, right? This is going to go down. If this is going to go
Yes,
down,
sir.
this means this means that it is energetically favorable for a dislocation to travel on a slip plane in a slip direction. Correct?
Yes, sir.
Got it? Yeah. Okay, so you can also
Understood.
read more about it. So since it's a very less hour class, I just wanted to give you a brief idea. So just quickly moving on to the next slide. Now, why sleep on the closed pack plane? Because I briefly discussed about it, and now just very small thing to show you. So if I show you a crystal, this is a crystal before shearing. Okay, it's a crystal where there is no shearing which is going to occur. Now the second case is that now I consider this QR. This is another plane of atoms. So for example, this, if you consider this to be, in 3D, this is the plane of atoms. In 2D, this is a line. You see, this is a line in 2D, and in 3D, if you extend it outside the board or inside the board, it's a plane, right? So, so considering this is 2D, what happens is that QR is nothing but the non-closed pack direction. For example, suppose this is just a schematic. So Mn, if Mn is the most closed pack direction, and QR is not the closed pack direction. So in this case, and here B in this case, in the B case, so considering the two atomic layers which are which are not close packed, and these planes, I mean all the number of all these particular planes are close packed, and such that there is a shear acting along certain planes and there is no shear acting along the other planes. So in this case, what you will find is that, so this is quite confusing for you, might be quite confusing for you. So just to simplify all these things what I've said, see, dislocations are always associated with strain energy, right? Because see, in thermodynamics, the first law of thermodynamics, whenever you deform, whenever see, energy can neither be created nor be destroyed, it can only be transferred, right? Correct. Okay, so if that is the case, this means that a particular material, when you deform, what you are essentially doing, you are essentially applying some mechanical energy to the material, and that energy is going to be converted into strain energy in the material, right? Strain energy, because essentially you are distorting the lattice, and basically that will manifest itself in the form of strain energy. And this strain energy basically depends on the Bogus vector, because how, so this is the way. So I think this is not the right way of representing that the strain energy. This should be represented by capital E. Make a note of it. Is directly proportional to the square of B. That is the Bogus vector. Okay, the square of the Bogus vector. Okay, so the greater the Bogus vector associated with the dislocation, the higher will be the strain energy. So obviously, any material will definitely love to minimize its overall energy, right? Every material in the universe will like to minimize its overall energy. So if overall energy has to be minimized, this Bogus vector has to go down. Right? The Bogus vector has to go down, which means that obviously there is, so obviously on the slip direction, the definition again is supported, because in the definition what I said, on the close packed plane, okay, there is a certain direction known as the slip direction, on which the planar not a planar, the linear density of atoms has to be the maximum. Correct? Linear density of atoms has to be the maximum. This means the spacing between the dislocations has to decrease. If the spacing between dislocations decreases, which means what? The distance by which dislocations will move during plastic deformation, that decreases. If the distance between the by which the dislocations will move during plastic deformation, that decreases, what happens? Strain energy is reduced, huh? Because if this is going to go down, this is also going to go down substantially. If this is going to go down substantially, the structure becomes more stable. So that's the way you can understand this. So now, based on this, based on this, we can say that dislocations actually, those dislocations which are the smallest Bogus vector have the minimum strain energy. Correct? Okay. Where the B is minimum, the strain energy is also going to be minimum for a particular dislocation. Because definitely dislocations, there can be many types of dislocations in a material. I'm not going to go into details of all. Just you can read through this book. Read it. I will also upload this material once the class is over. So with this, you can do that. So now I give you a task. Okay, it's very simple. FCC unit cell, you guys all know, right? How to draw. Last time I made you draw that. Yes or no? You can unmute and speak.
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
Okay. So now what I want you to do is that, can you identify what is the close pack plane and what is the close pack direction in FCC unit cell? You have 10. I will give you a homework also, so don't have to worry. So okay, good. So see, this is your most dense. This is your close pack plane. See, this is a close pack plane in case of the FCC unit cell. Okay, so these are all the phase shifted atoms and all. So this is your slip plane, the most close pack plane. Okay, and within this close pack plane, all these directions, this direction, this direction, this direction. See, this is 110. See, all these are family, na? 110 family, because FCC all the
Yes, sir.
yes, so all the so all these what to say, directions are equivalent, because all the sides are equal and all are equal to 90 degree. Only in cube. If it is not cube, then this will be different. Like these two will be same, but this will be different, right? This cannot be the.
Yes, sir.
So that's what. So in cubic example, since you have around, you have 3-4 volt axis of rotation. I think you might have learned about it. So or 3-fold axis of rotation. As a result of this, all the sides are equal and equal to 90 degree, and angle between each equal to 90 degree. And in that case, what happens is that you will have all these, the sides of the rectangle be acting as a slip direction, 110 direction. So basically, if it is 111, like see how. So okay, to you, 111. How many planes are you aware of? How many?
One is that one plane only, right? That
Right.
triangle one.
Yeah, but in a cube, how many 111 planes are you aware of?
Okay. If you take every edge, like every of those corners, 8 corners, so 8 such will be there. But
Okay. Yeah, correct.
Four.
4. Yeah, 4, because I tell you, for why I tell you. See, 8 is also correct, 4 is also correct. See, 8 is basically a total, right? It's a total number. But but what happens, you see, if it is 111 and I'm taking 1 bar 1 bar 1 bar 1, okay, means
yes, sir. Then
so this is like
parallel planes.
parallel planes. That's the reason we for our calculation So I mean, how many slip systems are there? We take 4. But total, you are right, because in total it is 8. But partly Aditi is also correct, because that is one bar one. I mean, bar one, bar one, bar one, and 111. So they are parallel. So we cannot consider both, right? So that's what. So similarly,
Sir,
if you are,
what is bar one? Like bar.
you see, minus one, minus one, minus one. In crystallography, we call minus one as bar one, actually.
Okay, sir.
Minus one, na, means see 111, and there is minus one, minus one, minus one. So minus, we don't write, we don't call it minus in crystallography. We call one bar or bar one. I mean, we put a bar on top of one. So that's what we call it. Okay.
Okay,
So
sir.
fine. So, good. So if that is there, and okay, good. So can you tell me, like, from here, just looking at this figure, how many 110 planes are here? I mean, crystal
3
three.
3, like
Okay. Yeah,
or
correct. But
3 count.
6 actually.
yeah, but is it 6, or is it how much? Exactly, is it 6 or how much?
Wait.
6, I think.
6. Just again rethink once. How many possible combinations of 110 can you have in cubic?
4, sir.
No, not 4. 6 is partly correct. I told you, no, last time. 6 is partly, like 4 was partly correct in the
Sir,
last.
is it 12?
Ah,
Is it
why?
12?
Yeah, why?
Because one bar and zero, like zero can be in three places, right? So 3 into 2 into 2, something like that.
Yeah, that's correct. Right. So that's what. So you have totally around 110. I mean, totally 12 110. But out of that, you have, you don't consider parallel things. Okay. As a result of which you consider take only 6. But that is not like just a question that is not relevant here, because this will come in the next slide for the BCC unit cell. But that's okay. Means for this particular plane, for this only one particular plane, if you take 111 plane, and this is not a family. If you take a family, means total there are 4 slip planes, and each plane will have 3 slip direction in FCC. So there is this 110 direction. See, because in every triangle you cannot have total 6, na? You cannot have 6 110. You can only have 3 110 in a particular 111. So as you have seen, there are total 4 slip planes. A slip direction in every slip plane is equal to 3. That's the thing. So that in total there are what? So the slip system is 111 110, like HKL UVW, and the total number of slip systems is 4 into 3. That's 4 111 and 3 110. So 4 into 3, because each has 3. Each 111 has 3 slip direction, and total comes to around 12. Okay, this is what. Right? You guys are clear with this? Any doubts, please ask.
Yes, sir.
Any doubts, please ask. Okay. I think if you are clear, then can we proceed towards BCC? Can you do the same thing for BCC now? Draw the close pack plane and close pack direction for BCC. You have exactly, I don't have much time. Maybe I can give you 6 to 7 minutes. Okay. 6 to 7 minutes for this. Just do that and I can quickly show you the answer then. Okay. You're trying.
Sir, is it 110 plane?
Yes. Okay, now let me see. Can you show me that how did you draw it? I mean, just uh, wait. What is a right. Okay, now identify the slip direction from here. Aditi is showing something. What is this? Slip direction. Wait. Yeah, 110. Akhya, this is correct. Right, and 110. Right. 110 is okay. So just identify slip direction now.
Sir, I've done that. I got.
Okay, tell.
One second,
Yeah.
sir. I got 1 bar 1 1.
1 bar 1 1. Okay. Okay. Yeah. Correct. Yeah, that's right. So can you just show it?
So I guess there'll be like 2 for the slip
What is 2?
direction 111, and the like if you take that body
Right.
the
Right. See, that's what I'm saying. So if
so
you take
111 and
uh, uh, correct. So how many slip systems now do you have in BCC now? If
the top body then like the bottom part.
how much?
12, right? 12, right?
12. 6 into 2, right? But this is see that's what see BCC things
12
are not as
system.
simple as FCC because I will tell you, but I mean this is you are right. I mean all you guys are right. It's not wrong. I mean in 110 111 slip system there are only 12, but I will also show you the other cases where you also might have other slip systems activated as well. I mean it's not always this is the slip system which is the most commonly activated because again there is slip system activation. This will be taught later, but this is what. So in FCC basically what you have, this is your 110, right? This is our 110 that you guys have drawn, and in this so within this what you have is that this is this body diagonal. This body diagonal of the cube is basically going to be your slip direction, correct? 111, this is going to be your slip direction. Okay, so if that is the case, so there are total 6 most close packed plane 110, and this most close packed direction in each 110 is equal to 2. So this means so basically you generally have this kind of slip system which is activated. This is total 12. Similarly, you can also have the other kind of slip systems 112, 111. There are also 123, 111. I mean, you don't have to that much think about it now, but for your information, this is not the only slip system. I mean, this is the most active one, but there are also certain slip systems operating at different stresses and also sometimes at different temperatures and in different materials. Also, this happens. So so basically so the total number of slip systems is equal to 48. Why I tell you this is equal to 12. This is here 112, 111. There is total 6 112 planes, and there are each will have 2 111 plane, direction. So 6 into 12, that is 12. So 12 plus 12 is 24. And here 1 2 3 so this is a very high index plane, right? These two are basically very high index planes. Now 1 2 3 there are 6 into 4, there are 24 slip planes. 24 1 2 3 slip planes which are possible if you have different combinations of these numbers. Permutation into simple combination, and you find that 6 into 4, that is 24 into I mean not 6 into 4, that is 6 into 4. I mean this total 6. I made a small mistake. There are basically total 6 slip systems only available. That there is 6 into 4. I mean with this combination you have 6 into 4 slip systems, means 24 slip systems, means 12 plus 24 is 48. Total 48 slip systems you have in BCC. But the question is now that and I will show you basically about so this is the table. You can make a note of it because one can take snapshot or whatever you feel. You can take a note of it, make a note of it. This is the slip plane, slip direction. There are these are the slip systems. Unit cell geometry. This will be helpful for your next studies also. So you can just take a note of it. You guys understood, right? What I wanted to say, or yeah, yes or no? No.
Yes, sir.
Yeah, take a note of it, or take snapshot or something. Do that. Yeah, you can take it. You can take it. No, from the screen. You take a snapshot.
So take a snapshot.
Take a mobile and take a snapshot. That's it. Okay, now one question to you guys is very simple question is that I want to ask this. See, I am telling that in FCC there are 12 slip systems. Okay, only 12 slip systems. And in BCC I am talking that there are 48 slip systems, but the most, if you consider the most close packed slip system 110, 111, there are only 12, correct? But the question is now that if you take now I will ask the question like this. So if you have an FCC material and a BCC material, which out of the two materials you will find to be the most ductile? You have an idea? Any idea on this? Why? Okay, why? Good, correct. Why?
Is it the FCC one? sir also said in the class that the gold is more ductile, it's FCC, and tungsten is BCC, but yeah, not that ductile.
Why? Means, can you any ideas? Small.
It's it's
Let
more
me.
close packed, so there is more room for
Yeah, yeah,
distortion.
Yes, sir.
yeah. Correct. Maybe it's yeah. There is more not room. See, in science you cannot say more room for distortion. Rather, you should say as it is more close packed, these locations can easily move, right? These locations can easily move, right? Because see,
Yes,
that's
so
what I
that's what I meant.
yeah, the shorter the distance between atoms means the more close packing means dislocations have to cover much less distance. For every step when they do, they do during plastic deformation. That's the reason why it is why. So there's a very interesting question is that why even BCC with 48 slip systems and this is 12 slip systems only. Why this is more ductile than this one? This is a very interesting tussle in science actually. This is one thing. Okay, another question to you is that have you heard of alpha iron? Has Pradeep said thought of alpha iron or something? For iron carbon phase diagram, I think he has thought of alpha, no? Alpha iron. Has he thought of that?
Yes, sir.
Yes, sir.
Okay,
Yes,
okay.
sir.
Now can you tell? Yeah. Now in the left hand side of that phase diagram, there is something called alpha. I mean alpha ferrite, no?
Uh,
Just think
well,
alpha ferrite. Okay, don't have to think about alpha ferrite. Think of alpha iron, simple alpha iron. Okay, simple alpha iron. In alpha iron, it is highly ductile. No? Iron at room temperature is highly ductile, right? Correct.
considerably. I mean, not that much, but yeah.
Okay, but okay now, but I've already said that FCC metals are comparatively much more ductile as compared to BCC. But then, why do you think this alpha ferrite, like when I'm adding carbon to this alpha iron, for example? Okay, so when I'm adding carbon to alpha iron, which is to form the alpha ferrite. Okay, so why do we call that alpha ferrite is the softest phase in the phase diagram, right? Because BCC, if this is not as ductile, it should be hard, na? Why it is I'm calling it as a softest phase in the phase diagram?
Maybe
Idea?
because that when the carbon atoms they get added, they go into those interstitial voids.
Okay,
So
okay.
because that the closed packing of the system it increases, and
Not exactly, not exactly. There is something other than that happening. Okay, see, if the carbon atom goes to the octahedral voids, like there is I talked about the voids, no, in the earlier class. So if they go into the
yes,
octahedral
sir.
basically, and they cause the tetragonal distortion. There is something to read it yourself, I think better. It's called tetragonal distortion. Once this tetragonal distortion happens, carbon basically strengthens up your material, but at the same time, see, the carbon is going to go there. Now carbon itself is having an atomic radius is very small, no, as compared to iron atoms. If it is very small, means there is a size difference. If there is a size difference, there has to be some lattice distortion. If there is lattice distortion, there has to be some strain, right? There should be strain in the material. Strain means that strain will harden your material, right? Because it will make it more difficult for you to not deform that material. But the only thing, but why do we see it as a highly ductile phase? See the so you can think about it. You guys can think about it. So based on today's understanding, can you correlate today's understanding with this alpha ferrite or not? I mean, is alpha ferrite an exception or not? So you have to think. I mean, this is something you have to think. Brain. You have to apply your brain and find it out. It's a very simple thing. But just think. Search for literature if you want. Okay, got it. So yes or no, you guys.
Yes, sir.
Okay, good.
Yes, sir.
Okay, so for your so now your homework is as follows. So now about about all this in FCC and BCC, you have to do the same exercise for HCP unit cell and find out what are the slip systems in HCP. That's the homework. Okay.
Yes, sir.
Okay, so you actually taught how to draw an HCP unit cell. No, that is not a problem for you. I think then you can give a try. Once you know about HCP unit cell, I think this is also available in many textbooks. But first read about them, understand them, and then do it, because in finals you might get questions not as straightforward as this. So maybe okay.
Yes, sir.
Okay.
Okay, sir.
So okay, fine. So okay, I think now time is also up for you. You guys before leaving, just give your attendance. Give your attendance in that Google Classroom so that we can mark you present. Okay. Just type your roll number to today's date and type present one, because when you entered it was present, and now you put present one. Okay. And submit the homework definitely before next class. Okay. Before the next tutorial session. Okay.
Okay, sir.
Okay, you guys can leave now. But give your attendance. Okay, there. Don't forget.
Thank you, sir.
Okay, welcome. You're always welcome.
Thank you, sir.
Yeah, Kath, you wanted to say something or?